Hello, welcome everyone, and thank you for joining us for this episode of Spectroscopy in Action, our live webinar series. My name is Paula, I'm the Marketing Account Lead at Edinburgh Instruments, and today I will be joined by two of our application scientists, Grant and Tommy. Together, they will be presenting our webinar, How to Measure Quantum Yield with an Integrating Sphere. Grant and Tommy will be showing you how to use an integrating sphere, which has revolutionised quantum luminescence, photoluminescence quantum yield measurements, making them faster, simpler, and more accurate than ever before. They'll use real experimental examples to teach you how to measure absolute PLQY and give tips for avoiding the most common mistakes, as well as explaining how these experiments have been simplified by modern calibration techniques and data analysis software. At the end, we'll have a Q&A session so you'll have a chance to ask any questions you might have. Hope you enjoy this webinar. I'll now pass over to Grant and Tommy to get started.
Yep, good morning everyone. As Paula says, today Tommy and I are going to be teaching you a little bit about quantum yield and how we measure it at Edinburgh Instruments. The topics we're going to cover are the basics of photoluminescence quantum yield. We'll discuss a little on the difference between the relative and absolute methods, explain how to measure the absolute method with Edinburgh Instruments, and then how to identify and overcome some problems you might face if your samples are a little bit difficult. So firstly, what is quantum yield? Quantum yield is the metric which is used to discuss the efficiency of photoluminescence. It's defined as the number of photons emitted divided by the number of photons absorbed, and typically converted into a percentage. A sample which has a 100% quantum yield will emit a photon of photoluminescence for every single photon absorbed. It's an important characteristic for people working in many applications, from display technologies to chemical sensing, medical imaging, and photovoltaics. It's typically split into two methods when it's presented. One is the relative quantum yield, and the other is absolute quantum yield. Relative quantum yield compares your sample to that of a known reference sample. This is why it's called relative. It's the most accessible quantum yield technique and can be performed with some very simple spectroscopy setups. And the procedure is as follows. The first step is to select an appropriate reference sample. We then need to measure the absorptance of our two samples, the reference and our unknown, determine the emission of our two samples, and then calculate the results. So how do we select a reference sample for this method? The ideal reference sample absorbs and emits in the same spectral wavelength ranges as your unknown. It has well-characterized or a certified quantum yield, and it will have a quantum yield similar to the unknown sample. The reason that we would like a similar quantum yield is so that the same spectroscopy parameters can be used to get good quality data for both. So the first step is typically to measure the absorptance of our sample. Absorptance is defined as the proportion of light absorbed at any given wavelength. Typically, a spectrophotometer will measure in units of absorbance, which is logarithmic, and we need to convert this to the proportion of light using the equation you see there. The absorptance is equal to 1 total absorption minus 10 to the negative absorbance. We then also need to measure the photoluminescence emission of our two samples. This is typically done on a different instrument, and we scan, we measure the emission scans at our chosen excitation wavelength, but it's important to know the excitation flux, the actual number of photons hitting the sample if the excitation wavelength is different for the reference in the sample. And I'll explain this when we see how to calculate our results. The relative quantum yield calculation looks a little bit daunting there, but it's fairly simple if you break it up into its terms. You have the photoluminescence quantum yield term. So in this instance, quantum yield of our unknown sample X is equal to the quantum yield of our reference sample multiplied by some scaling. The first term you see in this equation is the emission term. This is the integral underneath the emission spectrum of our unknown and our reference. The next term is our absorbance term, and this is the proportion of light absorbed at the excitation wavelength. The next term is our excitation term. This is the actual flux of light that the samples saw during the measurement. If this is the same wavelength for both your known reference and your unknown sample, then this term would cancel to 1, assuming you can use the same measurement parameters. And that's why the reference sample selection is such an important step. And then we'll follow this up with the refractive index term. Again, if our reference sample and our unknown sample are in the same solvents, this term also cancels to 1. However, if this is not the case, then we make this calculation more and more complicated. There are some limitations of the relative quantum yield method, as I just hinted at. One of the first ones is the reference sample selection. This is typically not too difficult for working in the visible region. There's many well-characterized fluorescent samples at this range now. However, once you get into the NIR, you'll struggle to find certified samples, and then the quantum yield of things like quantum dots can vary based on preparation methods. The other big issue is the steradium problem. Essentially, the relative method only works accurately if samples emit isometrically. They emit the same in all directions. But if you've got a sample like a thin film, something which might have waveguiding properties, or only doped in specific places, then this emission is not the same in every direction. Because we can only put the collection optics of our emission in one place, then this will drastically change the quantum yield based on what intensity of emission it's seeing based on the direction the detection optics are at relative to the sample. So how can we overcome this problem? An integrating sphere solves this. So how does an integrating sphere solve this problem? Essentially, it allows us to harvest light in all directions simultaneously. It solves the problem of reference sample selection because we're able to harvest all of the unabsorbed excitation light. And this allows us to calculate the absorbance, and we're able to harvest all of the emission in all directions, which allows us to get our emission terms. So how does an integrating sphere let you do this? Here we have a schematic of our QI Pro, and we see that the sample is mounted internally to the integrating sphere. The light hits the sample, and then unabsorbed excitation is scattered, and the emission comes from the sample. However, you'll see that there is a baffle between the sample and the emission port. This forces the light to be reflected within the sphere, and the reflective coating of the sphere itself has very diffuse reflectance. The result of this is that the emission light and the scattered excitation light is homogenized from all directions before exiting the emission port towards the collection optics to be counted. So I'm going to pass you over to Tommy, and he's going to explain how this allows us to activate the absolute photoluminescence quantum yield method.
Thanks, Grant. So yeah, in this part of the presentation, I'll go over the absolute PLQY method and go over how to measure it using the Fluorical software. So PLQI, as Grant mentioned, is measured by measuring the proportion of light that's emitted versus the proportion of light that's absorbed. In the absolute quantum yield method, in practice, this is measured by measuring the emission of your sample versus the emission of the blank, which is divided by the scattering of your blank minus the scattering of your sample. And this allows us to calculate PLQI from as little as 2 scans, making it much, much more simple. So this spectra at the bottom here is the 2 measurements that you'll need to perform. So you'll perform a scan that collects both the scatter and the emission of your sample, and the scatter and the emission of a blank. And we'll go through the typical workflow for this measurement, which is preparing your sample, selecting your parameters, collecting the data, and then processing it to calculate the PLQI. So for liquids, your sample will typically be a solution, and the blank will just be the solvent of that solution. And when you're doing this measurement, you want to have cuvettes which are optically matched. So this means that they're made of the same material and they'll have the same optical properties. You also want them to be 4-sided, as this is an emission experiment. and if possible, having PTFE stoppers as good as these are not going to be emissive. The concentration that you want to have for your solution, you want to have the absorbance to be around 0.1 at the excitation wavelength, and this ensures that you're not going to try and minimize inner filter effects, but Grant will talk a bit more about that later on. You also want to try and keep the volume the same for the blank and the sample, just so that they have the same optical properties. And so for a 10 millimeter path length cuvette, this is a minimum of 2 ml. For powders, we have these little powder trays where you can place your sample in. And it's good to prepare these well away from your integrating sphere, as you just want to avoid contamination of the integrating sphere as much as possible. So you want to just add enough powder so the bottom of the tray is completely covered. It doesn't have to be completely full. And then you want to seal that tray with a quartz cap, as well as the blank, to ensure that it's a fair test. And it's also good practice to clean and dry any external surfaces just to avoid any potential contamination. So the next step is to then choose your excitation wavelength. So it's a good practice to characterize both the absorbance and the emittance of your sample before you start your PLQY. This allows you to then pick an excitation wavelength where your sample is going to absorb, and you crucially want to choose an excitation wavelength that's not going to overlap with the emission region. So in this example on the right here, the onset of the emission begins around 450 nanometers. So we're going to choose an excitation wavelength, which is 10 nanometers before that. The next step is to choose your bandwidth. So unlike a typical fluorescence experiment, we're going to choose our parameters based on the excitation peak, as this is going to be the most intense peak in this measurement. So you want to set your bandwidth so you're not saturating your detector, but you also want to get good signal to noise ratio in the emission region. But we'll talk a bit later on about how to measure samples that have very, very low emittance. And typically for these experiments, we recommend using a wide excitation bandwidth and a narrow emission bandwidth so that you get good resolution in your scattering peak when you're integrating. So once you're happy with that, you can then select your parameters. You want to ensure that you have any appropriate corrections, such as a background subtraction, emission correction, and the inappropriate emission correction file. You want to choose your scan range so that it covers both the excitation and emission peaks. So we recommend that you start 20 nanometers before the onset of the excitation and end 20 nanometers after the end of the emission. The step size we recommend to be equal to or less than 10% of the widest bandwidth. So for example, if you had a 5 nanometer excitation bandwidth and a 0.5 nanometer emission bandwidth, using a step size of 0.5 is appropriate. You can also adjust the signal to noise ratio by the total integration time. So you can adjust this by changing the dwell or the number of repeats. So now I'm going to give a quick demonstration of what the data processing looks like in our Fluorical software. So I'll just switch over now. So here we have the two scans of the blank and our sample. The sample is a fluorescent dye in ethanol. And we can see that we have covered both the scattering regions and the emission regions. So once these are in the same scan, we can open up the PLQY wizard. This sample was a liquid. We did a direct only measurement, and the scattering and emission peaks were measured at the same time. So the software will automatically assign the blank in the sample, and we can just confirm that by pressing validate. And the software will estimate where the scattering region is. So it's just left up to the user to then define the emission range, and we can press calculate so that we have calculated PLQI of 95%. So I'll hand over to Grant to some of the difficulties that you might come across when you're doing PLQI in terms of sample reabsorption and how to correct for that.
Thank you, Tommy. So one of the things that Tommy mentioned during sample preparation of solutions was that we need to get the concentration just right to avoid the inner filter effect. So I'm going to teach you how to correct for what's called sample reabsorption. So sample reabsorption is based upon the inner filter effect, and the inner filter effect is typically split into primary and secondary. The primary inner filter effect is essentially when a sample is so high concentration that the excitation light can't penetrate deep enough into the sample to reach the focal point that we are collecting the emission from. When we're using an integrating sphere, we don't have focused collection optics, so we're not so fussed about the primary inner filter effect. However, we are concerned about the secondary inner filter effect. The secondary inner filter effect is defined as the sample absorbing its own emission light. So this is common in samples with low Stokes shifts. So the sample that Tommy presented was a rhodamine 101 in ethanol, and the example that I'm going to use is rhodamine 6G in ethanol. As we can see, these rhodamines have quite low Stokes shift, and there's quite a significant overlap from 520 to 580 nanometers between the absorbance and the emission, which means that rhodamine can absorb its own emission. This is particularly problematic when using an integrating sphere because the emission is harvested in the sphere and reflected multiple times, which means it can be re-exposed to the sample. This leads to an underestimation of the true emission spectrum, and therefore an underestimation of the quantum yield. So how can we identify reabsorption? To identify reabsorption, we need two things. We need the observed emission from our sphere, and this will be the blank subtracted observed emission. So we take the emission region of our sample and subtract that from the blank. And then we need the true emission. So that measures outside this. So this is measured in normal cuvette geometry. I've also blank subtracted it, and we've been conscious to use a really low concentration sample and long integration time to ensure that this isn't affected by reabsorption. So I'm going to hop into Fluorical and show you in real time how we would identify sample reabsorption. So here in the top panel, I have the quantum yield data that I recorded for my rhodamine 6G sample. And in the bottom panel, I have the normal cuvette measurement using a lower concentration solution, which we're using as the true emission spectrum. So the first step is to actually calculate the quantum yield and to extract the emission from within the sphere. So this sample was a liquid, measured direct only, and it was only measured in 2 scans as the scattered excitation peaks and the emission peaks are on the same spectrum. This launches the wizard, which automatically assigns blank and sample, hit validate, check my scatter range, and define my emission range. I then hit calculate, and we get quantum yield of 94.3%. If I come into this sample emission tab, which now unlocks, we can see the blank subtracted emission spectrum from within the sphere. And if I tick open emission scans in Fluorical, when I close the quantum yield wizard, I will now have the rhodamine 6G from the sample. If I minimize my quantum yield data and I hit join, I now have my true emission spectrum and my spectrum from within the sphere on the same active window. I can grab my cursor tool and place this somewhere in the red end of the spectrum and click normalize at wavelength. And I'll just normalize them to 1 at this wavelength. This produces this data here. So can we identify reabsorption from this? The answer is yes. What we have is a great match in this tail emission part where the rhodamine is not absorbing. And then as we get towards the area where rhodamine absorbs, we start to see that we're losing a significant portion of our emission. So we've identified reabsorption, but how do we use this to correct the quantum yield? So I'll come back into the slides and I'll show you. So like I said, we've identified reabsorption, and we did this by having a good match in our red end of the spectrum where the sample is not absorbing. However, we see a mismatch in the blue end of the spectrum where the sample can absorb. So the first thing we need to do is to quantify the reabsorption. How much of our emission did we lose? And we do this by taking the integral of the true emission minus the integral of the observed emission, which leaves us with this small gap here between the orange and green lines. And we divide that by the integral of the true emission spectrum. This gives us our proportion of light which has been lost to reabsorption, which in this instance was about 12% or 0.12. We then plug that into this equation here. So the true quantum yield is equal to the observed quantum yield divided by 1 minus the proportion lost plus the proportion lost times the observed quantum yield. In this example, we had 94.3 when I calculated in real time in Florical. When I did this preparing the slides, we got 94.9, just picking slightly different ranges. And then we divide this by 1 minus our scale factor plus the scale factor times the observed quantum yield. And we see that this corrects to a true quantum yield of 95.5%. This isn't a dramatic difference in this instance, but this is because the sample has a high quantum yield. Essentially, these reabsorbed photons are very likely to be re-emitted as photoluminescence again. However, if you have samples with 30 and 40% quantum yield, you can find quite a dramatic change when you perform this reabsorbance correction. One of the next problems you might encounter is the measurement of weak samples, and I'll pass you on to Tommy to explain how to handle that.
Thanks, Grant. So yeah, a common problem for people is how to measure PLQY when their sample is weakly emitting. And the problem with that is that weakly emissive samples will require excitation light that is very intense. And this can often cause detector saturation when you're measuring the scattered excitation peak. So the solution to this is to split the measurement into two parts, where you measure the excitation region with a neutral density filter, which is going to attenuate the intensity. And then you can measure the emission regions as normal without the filter. And then you can do a bit of mathematics to then undo the effect of the filter by scaling up the scatter peak intensity. So the first step to do is place your sample in the sphere, and you want to set your excitation and emission bandwidths to give adequate signal to noise in the sample emission region. You then want to place the blank in the sphere and place your proposed neutral density filter in the excitation pathway, and check the signal to ensure that it's not saturating your detector at the scattered excitation peak. So once you've done that, you can collect your PLQY data, collect your emission as normal with no neutral density filter, and measure the excitation region with the neutral density filter in the emission arm of the spectrometer. The final thing to do is then determine the scale factor to show how much the filter was attenuating the light. So to do this, you can do this by placing this in an absorbance spectrometer and measuring the absorbance at your excitation region. So you can see here at the top that the absorbance at around 870 is around 1.04. And we can calculate the scaling factor by doing 10 to the absorbance at that excitation wavelength. So that's 10 to 1.04, which gives us a scaling factor of around 10.9. You can also calculate this by measuring the transmittance if you want to do it like that as well. So finally, to calculate the PLQY, the top half of this equation will stay the same, but you just include the scaling factor in the scatter region of this equation. So I'm going to give an example of when to do this, of a sample that's weakly emitting, and I'm going to use an example of upconversion. So upconversion is a process where certain materials can absorb 2 or more low energy photons and emit a single higher energy photon. And these are materials such as rare earth nanoparticles, which will absorb in the near infrared and emit in the visible. And these type of materials will tend to have very, very low quantum yield. The kind of applications that you can use upconversion materials for is medical imaging, solar photovoltaics, and security inks and encryption. So I'm now going to give a quick demonstration in the Fluorical software of calculating PLQY with a weakly emitting sample. So I'll just swap over now. So on the screen here, we have the two spectra, or the four spectra rather, of the blank emission, the sample emission, and then our sample scatter and blank scatter, which were measured with a neutral density filter of an O optical density of 3. So once we have all these scans in the same window, we can go back to the PLQY wizard, and we're happy with all these parameters. We're going to say that the scattering and emission peaks were measured separately though. So once we've done that, we just need to assign the emission peaks. So we assign the blank emission and the sample emission. We can validate. It will estimate the scatter region, and we just need to assign the emission region. We also want to apply the scale scatter scans, so for a neutral density filter. So the scaling factor here for optical density 3 was 1000. And we can calculate our PLQY, that it's 0.014%, so really low. But there we've done it, collected our data and measured the PLQY of this upconversion sample. So I'll hand back to Grant, who's going to go over doing correction for sphere background, how to do this correction.
Cheers, Tommy. So yeah, as Tommy described, some samples are quite weakly emitting and require really intense excitation. However, samples requiring intense excitation often lead to requiring sphere background correction. So what is the problem here? Essentially, when we require sphere background correction, it's because we see increased background signal during the blank measurement, where there should be no emission signal. It's common in highly absorbing, weakly emitting samples, and it comes from increased stray light in the emission pathway. Essentially, when you're using an integrating sphere and you hit it with really high intensity excitation light, all of that excitation light is captured and guided towards the emission optics. This leads to an increased background when you're measuring your blank because it's not absorbing this excitation light, and it manifests as an underestimation of your quantum yield. So how can we identify the need for sphere background correction? Here I've got some data of NATA and PBS, and as we can see here, in the region between our excitation and the onset of our emission, the blank signal and the sample signal don't match. Theoretically, they should. There should be the same amount of background signal in both measurements because the sample is not emitting and the blank is not emitting. But because of this increase of stray light in the non-absorbing blank, we see a mismatch. So essentially, how do we correct for this mismatch? What we need to do is we need to scale the blank emission down to account for this. So the quantum yield calculation becomes the sample emission raw minus the scaled blank emission divided by the number of absorbed photons. How do we determine this scaling factor? The scaling factor is determined as the proportion of light not absorbed by the sample. So it's really similar to the reabsorption correction. We're looking for the proportion of light not absorbed by the sample, and we get this using the blank scatter, the total flux of excitation, minus the sample scatter, and then divide this by the blank scatter. So I'll give you a demonstration of how to identify and what this looks like when we do this in Fluorical. So here I have a sample which is a really weakly emitting but highly absorbing perovskite thin film. And we can clearly see in this region between 600 and 700 nanometers, where the sample is not emitting, that we have a big mismatch between the background signal of the blank and of the sample. So if I hop into the quantum yield wizard, I tell it I was measuring a solid, again, direct measurement only. However, our scatter and emission peaks were measured separately. I'll launch the 4-scan wizard. I now need to assign my sample emission and blank emission and hit validate. Fluorocal's assigned my scatter range, and I can see that my emission range is actually more like this. So now how do we correct for this? In our new quantum yield wizard, it's really simple. We just need to tick this box here. We tick this box and we see our scaled background now in green, and we see that it's got a good match for the expected baseline out into the sample. See that it's matching here. I can then hit calculate to get my quantum yield, which was absolutely tiny for this sample. However, if we notice, just quickly, one more thing I want to point out, the scaling factor used for the background correction, 0.163, is the inverse of the proportion of light absorbed, which was 83.7% or 0.837. So this is how we determine the scaling factor that we use for the baseline correction. It's not always a perfect match. This is why we're allowed to tweak it here, but this is where we start from. So this is an example of how we'd apply sphere background correction. And then at the same time, if we'd measured using the weak samples method with filters, we'd have been able to do this correction all at the same time and get the results out of Fluorocal at the end. So to conclude, we discussed three main issues that you might experience when trying to measure the absolute photoluminescence of quantum yield of your sample. The first one was to identify and correct sample reabsorption. The next one was how to measure weak samples, which require intense excitation. And the final one was how to correct for the increased sphere background that can often happen when you use this intense excitation. We'll leave you there, but we're happy to field any questions that you've got. Thank you for your attention.
Okay, thank you, Grant and Tommy. That was really interesting. It was good to see the live demonstration. The question box is now open if anyone has any questions. We did have one come in already. So that is, can Edinburgh Instruments do the DeMello method?
Yes, yeah, Edinburgh Instruments can do the DeMello method. So the DeMello method is a 3-scan method, typically which involves the measurement of the blank, and then the measurement of the sample being hit directly by the excitation light, and then a measurement of the sample being outside the direct excitation beam. So the integrating spheres that Edinburgh Instruments sell, their solid sample holders come with both a direct position for this direct excitation part and an indirect position for this indirect measurement. You'll notice during the general settings window in Fluorocal that there was the option for direct and indirect. And when you activate this method, the quantum yield calculation has changed to match the one from DeMello's paper back in the 90s.
Okay, thank you. And we also have a question, what type of filters should be used for measuring weak samples?
So the filters for weak samples, typically we recommend reflective neutral density filters. So it was just a neutral density filter. And we put these in the excitation optics because then they're only blocking monochromatic light. And we recommend reflective just because they tend to be better spectrally across the full spectrum, closer to the number described on them. But we would always recommend when you're doing this weak correction method that you measure the filter on a spectral photometer and use the actual value at the wavelength you're working with.
Thank you. And I don't think we've got any other ones come in. Said thank you for a good presentation and a nice explanation. What about films?
Sorry, what was that?
So we said thank you for a nice presentation and good explanation. What about films?
Yes, we can measure thin films also. Sorry. Yes, so Edinburgh Instruments, the QI Pro and the SC30 integrating spheres come with the PTFE blanking plugs. Basically, if we place one of these in the direct position, we can then support films on top. For these standard holders, I think they can take films up to about a 20mm diameter ring and then about a 15mm square sample. However, we do offer custom film sample holders, which can hold larger films. And we also offer ones made of different materials if required, because you're worried about the coating coming off your film and contaminating your sphere and things like this.
Great, thank you. I hope that answers your question. So I think that's all for today. If you do have anything else you'd like to ask, you can email us at inquiries@edins.com. So thank you to Grant and Tommy for joining us today to share all about the PLQY measurements and insights into using Florico. This is our last webinar of the year. You can catch up with all of the other ones we've presented throughout this year on our YouTube channel, just using the Lives tab. Our webinars will be returning in 2026, so make sure you're subscribed to our newsletter to find out what we'll be discussing next year. And if you have any suggestions for future webinars, please get in touch again using the same email address, inquiries@edins.com. And finally, I would like to say thank you to our product and applications team for creating and presenting these webinars throughout this year, to Craig, our digital technical expert, for keeping things running smoothly. And finally, thank you to everyone for joining us today and throughout the year. We will see you when webinars return next year.